Welcome to Ask and Learn.
So here is a block of ice which has a mass of 15 kg. So this ice is kept in a large room at 20 degrees Celsius. So obviously this ice will receive heat from the room and melt into water at 0 degrees Celsius. So the heat gained by ice while melting will be equal to mass of the ice into latent heat of fusion of ice. Now as you know, the value for latent heat of fusion of ice LF is equal to 3.34. This is in SI, okay? Into 10 to the power 5 joules per kg. So 1 kg of ice requires this much amount of heat to melt into water at 0 degree. So if you substitute the value of M and LF in this formula for Q, the answer will be 5.01 into 10 to the power 6 joules. So this much amount of heat is received by the ice. So okay, now let's move on to the question: is the melting of ice reversible or irreversible? Now this much amount of heat is received by ice, right? This happens of its own. Now will it ever happen such like the same amount of heat comes back from water and gets into the room, freezing the water back? Can we have that? No. Unless any external work is done on the system, we cannot have the heat transfer from water back into the room and freeze the water, right? So this is an irreversible process. So irreversible. And what is the reason? Because the same amount of heat, not even less or more, okay? No heat can return back from water into the room. Never returns. Let me write this back to the room. To freeze water. Well, let me add this as well. Unless any external work is done, because if we do some external work like we do it in a refrigerator, then it is possible, right? If we use a refrigerator, so we have to make sure that no external work is done. Now the next question asks, calculate the net entropy change of a system during the process. So the entropy is changed in both ice and water, ice and room. So for ice, the change in entropy for ice, del S for ice, is equal to now change of or heat supplied to the ice upon the temperature of the ice system. So the heat supplied to the ice, it was 5.01 into 10 to the power 6, and the temperature of the ice was at 0 degrees Celsius. So remember to change that into Kelvin. That will be 273 Kelvin. This will be equal to 18351.64 joules per Kelvin. So this much amount of heat, this is the increase in entropy for ice. Similarly for the room loses it, right? The same amount of heat. By using the conservation of heat energy, the room should lose same amount of heat. Now, since it loses, let me write this minus. So minus 5.01 into 10 to the power 6. Now the temperature of room is 20 degrees Celsius. So should I write 20 here? Of course not. You have to convert this into Kelvin. Otherwise you will be ending up with a simple mistake, and you get minus 17098.97 joule per Kelvin. So what is the total change in entropy of the system? The net entropy change, let me write this del St, the total entropy change is equal to, just add these two. So this was increase in entropy and this is decrease in entropy. Now this, what is the net change in entropy due to this process? This comes out to be plus 1252.67. So this is the increase in entropy of the system during the whole process. Now, does this result is this result consistent with our answer in A? Yes, because for an irreversible process, the entropy, the net entropy should increase. So these two plus 1252.67 and our assumption of this to be irreversible process match each other. So this makes sense, right? Okay, so this ends the solution for this question.